So, welcome back. We are going to commence today the study of the actual things we want to study in this course, namely symplectic manifolds. And we're going to start our study by looking at the best of symplectic manifolds. These are the ones that have all the nice properties that we want to capture, generalize, abstract, and then bring into the domain of manifolds. And these things are called symplectic vector spaces. So today we're going to go through some linear algebra, beautiful linear elementary algebra that will tell us, and then we'll isolate the objects that we care about, we'll study their properties, and then we'll immediately generalize them to symplectic manifolds. So the first thing we want to study are things called symplectic forms. These are going to be quadratic forms on some real vector space with some properties. So in other words, matrices. So V in this discussion is going to be a finite dimensional vector space So how hard can this be? V is just naturally isomorphic to the real numbers, Cartesian product m times. So let V be an m-dimensional real vector space. So it's a real vector space, and let omega be a bilinear map. This is the prototype of all the objects we're going to study in the rest of this course. It's going to be a bilinear map, but it's not just any old bilinear map. It's going to be skew symmetric. It's skew symmetric if, when you put in a vector in the first argument, a vector in the second argument, that's always equal to minus if you did it the other way around. Should already start to ring some bells. We've seen things like this before in this course. Things that when you put in an argument, they exchange sign when you exchange the arguments. And then I'll squeeze in the for all u and v in the big vector space V. That's a symplectic, a skew symmetric bilinear map. When you stick in two arguments and exchange them, you just pick up a minus sign. Easy peasy, right? So here's an extremely useful theorem. This is an elementary linear algebra construction, but often they're the ones that have the most power and lead to the most insight. So it's always worth dwelling on the elementary foundations, because they're the things that ultimately you'll develop the most sophisticated generalizations of. So let omega be a skew symmetric bilinear map. question?
The basis u go to from 1 to k or from 1 to n?
Should the basis u go from 1 to k or from 1 to n? It should go from 1 to k. So the dimension of a vector space is m, and we have that we require that that these three numbers add up to m. So we require that k plus n is equal to m. We'll make a comment about that later. Yeah. Okay, let's make some comments on this theorem. What is it saying? It's saying you have, someone hands you a skew symmetric bilinear map. They give it to you, and then according to this theorem, then there exists a basis where k plus n is equal to m, such that this basis has these three properties. Firstly, these vectors u are orthogonal, to use the wrong word. They have a zero overlap with respect to this skew symmetric map with all the vectors in the vector space V. Then there's this list of E's and F's, and the E's have zero overlap with each other according to this omega, but the E's and the F's do have an overlap. They're kind of orthogonal. So the way we're going to prove this theorem, so firstly, this is, it's not clear if this is constructive or non-constructive at this stage, but we're going to prove it constructively. And we're going to use a slight variation of a very powerful trick in linear algebra, namely the Gramschmidt process. So this is, I've lost count of the number of times I've used Gramschmidt in research papers. It's just an amazing way to furnish an orthogonal basis, and then allows you to do computations. So we're going to generalize the Gramschmidt procedure. So step one is to find these u's. That's step one. So we'll deal with that first. So this, we can at least find the space spanned by these little u's abstractly by saying that this vector space U is the set of all vectors in our vector space which have evaluate to 0 when applied via omega to any vector in the vector space. All right, so that's the space actually spanned by the UKs when we get to it. And then it's a vector space, so there is a basis for U, and let that be the basis. Okay, So we've furnished the first k terms in this special basis. So you have to, at this stage, you already have to be a little bit concerned, is this indeed a vector space here? Is this a vector space? Let's have a look. So I'm not going to write down that it's a vector space, but you should be quickly convinced that it is. So suppose u and u prime in U, is there sum in U? Let's have a look. So we put in the sum into here, and since this is bilinear, oh, I didn't put that that's equal to 0. Since this is bilinear, then that's equal to omega of u v, omega u prime v. So sums are inside this space. It's bilinear, so complex multiples are in this space. You can check the other axioms of a vector space or a subspace. So U is a vector subspace of V, and there is a basis. So we're sort of roughly a third of the way to our basis. And now we're going to inductively build up this EJFK basis by looking at the complement of this subspace in V. So take V, realize it as a direct sum of U plus something else, direct sum W, whatever this W may be. And now we're going to begin the Gramschmidt type procedure on this. Vector space W. So just take some vector in W. Just pick one. Call it E1. Then there definitely exists an F1 in W such that omega E1 F1 is not equal to 0. Definitely exists. Why does it definitely exist? Well, if there was no F1 that had evaluated to not 0 in W, then that would mean that E had a 0 inner product or skew symmetric product with every vector in W and therefore belongs to U. So F1 is there, it's out there, find it. So F1 is not evaluating to 1, but you can rescale it. So everything's linear, so we know we can do that. And then we're going to define or build W1 is the vector space spanned by E1 and F1. So this is my notation for span. I think that's fairly universal notation, but just in case I've written out the definition there. Yeah, I suppose in a quantum course this could be rather confusing. Okay, but this is not quantum mechanics here, so this is linear algebra. Now we're going to build another vector space, omega, W1 omega. What is it going to be? Well, it's going to be everything that's orthogonal via omega with this space here. So it's the set of all W's such that when you evaluate the skew symmetric map on W and V, you get 0 for all V in W1. So this looks very much like the ortho complement, right? If omega was an inner product, not a skew symmetric map, then this would be the orthocomplement of W1. Everything orthogonal to, if this was a inner product, which it is not. It's a skew symmetric map. But the similarities are so close that we can sort of adopt this language. Now, there's some little exercises for you, just to keep you awake. Firstly, if you compute the intersection between W1 omega and W1, if it was like an orthocomplement, you'd better hope that this is 0, right? And indeed, the exercise tells us that that's the case. Certainly imagine how this argument might go, right? Suppose there is something in this intersection here. Well, then choose, it's some linear combination of E1 and F1, right, because it's in there. And then compute the skew symmetric map on your W, use linearity, run it over all vectors V, W1, and you'll see that the only possibility is 0. So another exercise for you, maybe slightly more challenging. Really is a kind of orthocomplement, because not only do these two subspaces, this is a vector space, right, obviously, but not only do these two vector spaces have 0 intersection, but when you take the direct sum, you really do get W. Oops, that's a 1 here. This is pretty neat. And believe it or not, that's the whole process. We're going to just repeat this over and over again. Because we're going to inductively define W2 by replacing our original space W now with W1 omega, and just do the whole thing again, over and over and over again, until we exhaust the dimensions of our vector space. Okay, so to proceed, by replacing W with W1 omega and repeat. And that allows you to build E2, F2, which we're going to call W2, and continue. And because the dimension of our vector space V is not equal to infinity, this process terminates. and we have ourselves this lovely basis. And at the end of all of this process, we've decomposed V as a direct sum of U, W1, W2, up to Wn. Now this is just the Gramschmidt process sort of specialized to this symplectic setting. So you think of omega no longer as an inner product. You think of omega, although it's not an inner product, kind of like an inner product, and you do what you would do in Gramschmidt. And there's the only sort of additional subtlety in all of this is that you've got this space U here at the beginning. U is like the trash space which deals with all the vectors that have zero inner product with everything. And indeed, it is in some sense the nasty subspace, because what we're going to do in this course is largely define it away. We're going to look at the setting where U is in fact empty. We have a remark. It's amazing the kind of deep insights you can get from elementary operations. So this one's a really good one. So the dimension of U, what we can observe is that although we've presented a basis, we've broken the symmetry of the vector space, so to speak, by choosing a specific basis, some things are invariant under this process. No matter how we chose E's and F's, the dimension of U is independent of the basis. Right? It has a coordinate-free definition. So this integer, dim U, is somehow an invariant of these skew symmetric bilinear maps. And what does that imply? Well, that implies that K, which is the dimension of U, is invariant, right? I just said it. For this pair of a vector space and a skew symmetric bilinear map. But that also tells us something about N, right? Because M is also an invariant of a vector space. So we learn that N is also an invariant. That's pretty neat. It's not entirely obvious. And we're going to call N, and give it a name, it's called the rank of omega, not to be confused with the standard rank. Yep.
I'm sorry, at which point in the proof in this generalized Gramschmidt process do we see that W has to be the dimension of 2n?
At what point do we see that the dimension of, in the Gramschmidt process, that, that W has the dimension 2n? Well, at the inductive step, we always get two vectors, right? So there exists, take E1, then there always exists another one. So at this inductive step, every time you apply it, you know that you're going to get the two vectors. One.
There's not said that they have to be orthogonal or linear independent. The E and F1.
The E and F1 are not said to be orthogonal or linear independent. So E is just an arbitrary vector in W, right? And then we know that there exists always an F that has that property there.
Yeah, but it could be the same one, and
It's skew symmetric, it can't be the same, so yeah. All right, and so that allows us to infer that this number here, this integer, is also an invariant, and we're going to give it a name. We're going to call it the rank of omega. It's related to the rank of omega as a matrix, no worries, by a factor of 2. So we can use this lovely basis to present a matrix representative for omega. So if you let M so if I define V to be U1 through the list of the basis vectors U1 through to UK, E1 through to En, and F1 through to Fn, then forming this matrix here, V alpha, V beta, we see that omega has a very particular form as a matrix. It's comprised of 9 blocks, or it's a 3 by 3 block matrix. And with respect to the first k basis vectors, omega is like really 0, right? Because no matter what you put in here, 0, you put in here, 0, it's always 0. 0, 0, 0. Lots of zeros. And in fact, this is the U part of the basis representation. It's 0 everywhere, here, 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 and here. It's also 0 here, right? If you put in E's, then omega of E1 with itself is 0, right? Because it's skew symmetric. Similarly with the F's. And if you put E and F, then you get delta, but then because it's skew symmetric, you get minus identity there. So this matrix always has this particular block structure. With respect to our nice Gramschmidt basis. Now these kind of matrices, they turn up sort of all the way through physics. But most particularly in quantum physics of like in Fock space, bosons, fermions, we see that the canonical commutation relations between the operators, say for some bosons, has this particular form. So I'll just make that as a pure aside if you're interested in quantum mechanics. The canonical commutation relations between the x's and the p's in quantum mechanics has the form of I times by some skew symmetric matrix. In particular, this part here is 0, usually. However, you can generalize the canonical commutation relations to include operators which commute with everything, and then you would have this form here. So there is just a purely aside remark if you're interested in applications to quantum mechanics. The canonical commutation relations involve a skew symmetric matrix, particularly special one. And indeed, it's this sort of, you can see these zeros here. It's natural to think, what's life like if there are no zeros? What if you focus on the special case where the rank is in fact m divided by 2? That's the task basically for the rest of this course. We're going to throw out these trash vectors and look at the special case. And it'll turn out that that works for, that'll give us all the necessary insights we need, because when we are faced with this more general case, because everything's 0, it's very easy to generalize everything we'll say to when we have zeros. So let's do that now. Let's restrict our attention not to just symplectic, to skew symmetric bilinear maps, but let's get now to the special subclass of skew symmetric bilinear maps called symplectic maps. So we're going to start with a skew symmetric bilinear map, omega, on our m-dimensional vector space V. Then we're going to use this map to build a linear operator from V and the dual of V. So this is where we can start to mimic the role the metric plays in Riemannian geometry. So what the metric does in Riemannian geometry is it allows us to identify, it provides us with an identification between V and its dual, which you don't usually get, right? This is not there's no canonical identification, so you have to pick one. So usually when you do Riemannian geometry, you have some metric in mind, which is an inner product, and inner products give you a nice pairing between V and V star. This thing is like an inner product, right? It's sort of an anti-symmetric inner product. And it does indeed also furnish us with an identification between V and its dual. And we're going to try and mimic the whole kind of Riemann story, but with these skew symmetric maps here. But there's an obstruction to this really working, and that's the fact that this linear map here, which depends on its argument V, and here I'm defining its action on a vector u in V by this equation here, there's an obstruction to us using it like we would an inner product, namely this map's got a kernel. It's the zeros here, right? It's a non-trivial kernel, so it's not really useful as in this form as a way to identify V and V star. There's stuff that can't be identified. That's why we now make this focus on this special subclass. All right, here it is. Here's the main definition now. Enough motivating. Let's get to it. here it is. Here's the main definition now. Suppose we have a skew symmetric bilinear map which furthermore has the property that its induced map between V and V star is bijective, so it's invertible linear map. Then it really is a good identification between V and its dual. That's equivalent to demanding that U is just 0, the kernel of this map. If you have such a thing, then this pair of a vector space and one of these special bilinear maps, that's called a symplectic vector space. So this is the main object that we wish to study for the rest of the course and generalize. We want to take its beautiful properties and then abstract them and put them on manifolds as well. Let's talk about some of the beautiful properties. Well, arguably the biggest beautiful property is this duality, right? So this is a bijection. So just how an inner product tells you how to join to relate V and its dual, so does a symplectic map. It gives you a identification of V and its dual, which you can then exploit in many of the ways that you would exploit an inner product. Let's take some more elementary yet very powerful results. Because K, which is the dimension of U, is 0 by assumption for symplectic vector spaces, that tells us that n, or in particular 2n, is equal to m, the dimension of a vector space. Well, what does that imply? Well, that implies that 2 divides m, so m is even. You can't have an odd dimensional symplectic vector space. Via Gramschmidt above, we have basis with just E's and F's. We don't have any U's. This is called the symplectic basis. And in matrix form, omega has this 2 by 2 block matrix structure like so. Well, that's a symplectic vector space. I've given you the objects of this category of vector spaces. Now let's look at the maps between them, but before we do that, I'll talk about subspaces. So if you have a vector space, you can have a subspace, right? That's easy enough to define. But for symplectic vector spaces, it turns out not all subspaces are alike. There are some subspaces that differ from other ones. For example, you could have a subspace of a symplectic vector space that is, well, also a symplectic vector space. That's possible. But you can also have subspaces that aren't symplectic vector spaces. So it's symplectic if when you restrict this symplectic form to the subspace W, it's non-degenerate or symplectic. So let's give an example. Just take the space spanned by E1, F1 with some symplectic basis EJ, Fk of V. So it's a nice symplectic subspace, because when you restrict this symplectic form onto this two-dimensional subspace, you see that it's got this characteristic form there. But there are other subspaces that are also in their own right quite nice. And those are subspaces, for example, where the symplectic form completely vanishes. And an example there would be the subspace E1, E2, for example. So you have to be a bit careful about subspaces. Not all subspaces are born equal. And we'll have good reasons to look at both symplectic subspaces and isotropic subspaces. These have to do with Lagrangians, as we'll see later. That's the objects. Now what about the morphisms? What are the maps between symplectic vector spaces? Which ones are we going to allow? Well, if you have two vector spaces, then linear maps are the usual morphisms between vector spaces. But here we have this additional structure of a symplectic form. So we have to restrict our linear maps, otherwise we might map a nice symplectic vector space to a non-symplectic vector space. So that's why we better settle on what morphisms we're going to allow. They're going to be called symplectomorphisms. Well, bit of a mouthful, but that's what they're called. Well, what is it? It's got to be a linear map. In fact, we're going to make it a linear isomorphism. Such that when you pull it back, the symplectic form on V prime, you get the symplectic form on V. And just to remind you of the pullback of a definition, that's this one here. So there's the symplecto, and then, oh yeah. When such a thing exists, then these two spaces are symplectomorphic. Here's an example of a symplectic vector space. And this is, as we'll see, in some sense, the only symplectic vector space. So let V be R to the 2n, and let Ej be all zeros but one in the jth position and Fj equal, this is nth position here, n plus j. So we've already seen this example implicitly. So we let this be the basis, and omega naught it's kind of interesting to wonder, what does a symplectomorphism from V to V look like? In matrix form. Then it's worth proving that the matrix form of phi, satisfies M transpose omega naught M equals omega naught. So such operators form a group. We'll encounter this group later on in this course. We will discover more beautiful properties of symplectic vector spaces as this course proceeds. But right now, let's just march on and get to the main object of study in this course, namely symplectic manifolds. It turns out we now have assembled enough background material to write down the definition of a symplectic manifold. And the motivation, before I write down the definition, is, well, a manifold is locally like a vector space, right? So there's this tangent space you can always associate to a vector space. So a symplectic manifold should locally be like a symplectic vector space. That's the motivation for the definition I'm going to write down. And we can answer this question by looking at the tangent space of a manifold and seeing, is there a symplectic form on that tangent space, a tangent space of the vector space? If so, then we should assert that the resulting manifold is symplectic. Now there's some additional properties we're going to demand to make it nice and smooth. That was the motivation. So how are we going to do it? We're going to let omega be a 2 form, because skew symmetric maps look awfully like 2 forms, don't they? They have 2 arguments and they're antisymmetric under exchange of the arguments. So maybe a symplectic manifold is simply something with a 2 form on it. You know, and what does omega do? Well, it acts on the tangent space at a point P, cross the tangent space at a point P, gives you a real number, and is antisymmetric, so it's almost everything we need. It's a skew symmetric map. We furthermore call this thing closed if, when you take its exterior derivative, you get 0. now we come to the definition. So we get to call this thing symplectic, this two form, if it's closed and gives you a symplectic form on the tangent space. So let's make transport already an obvious corollary of our Gramschmidt process to the tangent space. What does that tell us? Well, omega is symplectic already implies that the dimension of tangent space to the manifold is even. Odd manifolds need not apply if they wish to be symplectic. Now that we have a symplectic form, we can define a symplectic manifold. And that's simply a pair of a manifold in a symplectic form. Let's give the canonical example. We've already seen it. So choose the manifold R to the 2n. It's definitely a manifold. It has one chart. And then take coordinates x1 through to xn, y1 through to yn for this very nice flat smooth manifold. And we can now introduce a two form that has all the properties we need, namely just wedge up the dx's and the dy's. You can check that that's closed. Just take d of that, and you get 0, because the coefficient here in front of these basis vectors is constant in this coordinate chart. So this closedness expresses via Stokes' theorem that the coefficients here don't have any sources, like it's somehow divergence free, right? for this space here, we have a symplectic basis for the tangent space. I'm using x's and y's. So this basis is given by, like, do the ddx 1s up to ddx n's and ddy 1s up to ddy n's, and these are like the e1s, and these are the e-n's, so the f1s up to the fn's. And this is all at the point P. Yeah. Okay, that's a kind of like, that's the obvious example. But there's one other very interesting example I'll cover today. Shows you that symplectic manifolds deliver more riches than simply r to the 2n. So we're going to find out, and this is why this definition is very nice, it admits other manifolds that aren't obviously r to the 2n. So there is more than one kind of symplectic manifold. So the next example, this example is actually really rather special because it doesn't generalize in a nice way, but nonetheless it's a one that will pop up all throughout physics. So let M be the 2-sphere, not the circle, but the 2-sphere. Turns out that's symplectic as well. But warning, the 3-sphere and further is not symplectic. Well, why is this 3-sphere not symplectic? You should be able to answer this one straight up. The dimension is 3, so that's not allowed. But the 4-sphere, like, is it obvious? Is it not obvious that the 4-sphere is symplectic? Interesting question. So, how are we going to turn the 2-sphere into a symplectic manifold? We're going to realize it as an embedded manifold of R3. So it's just the set of unit vectors in R3, and tangent vectors well, they are just vectors that are orthogonal to the unit vector pointing to the point on the sphere. So P is a vector, remember? And, okay, great, I've defined a 2-manifold. We have a 2-dimensional vector space as a tangent space, but do we have a closed symplectic 2-form, or a symplectic 2-form on this sphere? For that we need to be a little bit careful. So if you experiment a little while, you'll come up with something like this. I mean, there's only one possibility. So omega p on 2 tangent vectors, u and v, is going to be defined to be the inner product, the R3 inner product, between the vector p defining the point on the sphere and u cross v. Standard vector cross product like that. So you can check, is it an anti-symmetric linear map on the tangent space? Well, it sure is, right? If I put v in the place of u and u in the place of v, then the cross product gives you a minus sign, so that's good. And it certainly takes pairs of tangent vectors to real numbers. Now, what about, is it closed or not? Let's see. Well, obviously it's closed. The reason this is obvious is if it wasn't closed, that would mean that d omega is not 0. But there are no differential forms of degree 3 on a two-dimensional manifold. The vector space is already zero-dimensional. So it's almost on its way to being a symplectic form. Yep.
Sorry, but could we use this process to make a symplectic manifold out of S6 because we have a cross product on R7?
Ooh.
But it's not closed, obviously.
Yeah. So the question is, couldn't we do this on on S6 because we have a cross product on R7? Quaternions, right? Is it closed or not? I don't know. Actually, I don't remember if there's another sporadic sphere that's symplectic. I don't remember. Either we can Google that offline, or I can come back to you next lecture with the answer. I have a feeling that it doesn't exist. It's because it's non-associative, right? The cross product. And well, I'll reserve I'll hold off on answering that question, but it definitely is not clear if it's closed. Hang on, or isn't it obvious that it's closed in S6? Same argument, right?
It's not. It's a two form. We have a 6-dimensional.
Ah, yeah, it's a two form. We have a 6-dimensional. Duh. Okay, yeah. So it's not obviously closed. Yeah. So I'll get back to you on that one. Or you can probably Google it right now and you'll have the answer. Okay, all we have to check is that is this non-degenerate? And then we have a symplectic two-form. And it is non-degenerate because if P, U cross V equals 0, then, because when P, U cross V equals 0, U has to equal not, and U is not equal to 0, then just take V is U cross P. I got that right. U cross P is pointing in the direction of V. Yeah. Okay, so a little bit more time to talk about symplectomorphisms, so then we'll have defined our full category of symplectic manifolds. It's octonions, not quaternions, isn't it, for S6. The quaternions is what gives us this. So it's octonions, and they're non-associative, so it's not clear. Oh, okay. So yeah, we have an answer from Google. S6 is not symplectic because, indeed, it's not closed. Omega, presented by these octonions. Definition. So we have two symplectic manifolds. When are they the same? So let phi be a diffeomorphism. So there's at least, we're going to talk about the equivalence of the equivalence of these two manifolds as we would manifolds, meaning that they've at least got to be diffeomorphic. An invertible, differentiable, smooth map between them. And this diffeomorphism is called a symplectomorphism when it takes the symplectic form across. It pulls back the symplectic form omega 2 back to the 1 on M1. So it's just like, it's got to be a smooth map between them and it's got to respect the symplectic structure. Done. So that's how we're going to do it. And now we're going to have arguably the most important theorem. I won't prove it. I certainly won't prove it today, and I'm not entirely sure if I'll prove it in this course. I'll certainly give some kind of argument at some point for why this theorem is true. Now, this theorem tells us that manifolds, symplectic manifolds, are always locally like our friend R2n. So this is arguably the most important structure theorem we have about symplectic manifolds. So let P be a point in our symplectic manifold. Then there is a coordinate chart called the Darboux chart. And I'll denote this chart as U with the basis, coordinate basis x1 through xn, y1 through yn, such that on U, our 2 form is exactly the one that we had before. There's no other possibilities. So you can sort of sense how this theorem might be true. Let's sense how it's true for symplectic vector spaces to begin with. So with the symplectic vector space, the Gramschmidt process presents us with this canonical basis, the e's and the f's. If you did that process on the tangent space to R2n, then you immediately find a coordinate chart where the two form looks like this. So the only sort of difficult bit to this theorem is that showing that for every chart around a point, for every point there is a chart around that point where you sort of smoothly can extend this Gramschmidt process. That's sort of one intuition for why this might be true. As I said, I won't prove it today, no way. It's a bit more sophisticated than that, but that's arguably the most important result we have on symplectic manifolds. So I think we'll stop here for today. In the coming lectures, we'll get onto Lagrangians and Hamiltonians and all kinds of good stuff like that. So, but for now, thank you very much.